Now that you've finished all your homework, more, yes, more.
Yeah.
Okay, I need like a test or anything. Outline for the final. Also, you didn't get these last time. I have last semester's test. You didn't get these last time. Same. It'll help.
Can you change?
To surprise you?
I'm surprised it's actually good, right?
Hey,
shopper.
Right. Where's the shop? Okay, today's Monday. We're watching Paulina. Okay, Archie. All right. Don. Okay, Cassie. Okay. Eric. Frank. All right. Andrew. Ben. Matt Davidson. All right. Okay, Annette. Cassie. Cassie, all right. Okay, Robert. Linda. Bobby. All right. Rafi. Here. All right. Merlin. All right. James. Okay, Rio. Okay, yeah, Rio. All right. Kang. All right. Francisco is here. Okay, here. All right. Scott. There. All right. Marco. Dennis. Okay, Asian. Okay, James. Hey. All right. And Rita. All right. Okay, Nassim. Okay, Sue. All right. Okay, Joe. All right. Richard. All right. Paul. All right. Leon. All right. Okay, Godfrey. All right. Okay, Francisco Medina. All right. Okay, Alex. All right. Okay, Lena. Oh, yeah. Okay, Jesse. All right. Toby. No. All right. And Don. All right. Will. All right. Roger. Here. Oh, no. All right. Mason. All right. Roberto. Chris. Shayla. All right. Marco Soriano. All right. Nick. All right. Okay, Kate. All right. Andy. All right. Marcos. All right. Kevin. John. All right. And Chen. All right. Anybody else? Leslie? Linda? Yeah. Okay, anybody else? Okay, so I know chapter 3's up here. Okay, we're just going to barely start 4 today. Just get that ball rolling. You have a test on Wednesday. Yay. All right, chapter 3 only. Yeah, like my Python. Yay. All right. Okay. All right. Well, test on Wednesday, chapter 3. We'll do then. Still have time for questions today too. All right. Okay, so chapter 4 is what books call applications of derivatives, which for us mean graphing. Okay, applications of derivative. Because when we think of useful applications, we think derivatives. All right, so 4.1. All right, these maxima and minima, extrema. Extrema of a function. Okay, high points and low points. Okay, hopefully Wednesday will be a high point for you, not a low point. What are extrema? Extrema are, again, maxima and minima. Maxima and minima. Maxima and minima. Right. Maxima corresponding to high values of a function, minima corresponding to low values of a function. All right. But are we talking about absolute or relative maxima and minima? All right, let's start off with some terminology. Okay. And we're at the stage where my online notes are very much like my handwritten Word notes. All right. Okay, terminology. So I just made up this function. All right. So I made up this function, x, y, right? Okay, whose graph looks like this. This guy's not going to be polynomial, I think. Okay. Maybe piecewise. All right. Okay. So let's say that here's x equals 5, x equals 8, not the scale. X equals 12, x equals 14, x equals 16. All right. And what are the like limits? Let's see. 1 here, 3 here, 7 here, and 10 here. All right. Okay, 5 points that I want to classify. Okay, over here, that looks like an interesting point. Let's call him point P. Here's an interesting point. Let's call him point Q. Here's an interesting point. Let's call him point R. Here's an interesting point. Let's call him point S. Here's a kind of interesting point. We'll call him T. All right. So let's talk about features of this function. All right, maximum and minima, and terminology. All right. Now, first of all, I guess before I say anything else, let's remember what it means for a function to be increasing or decreasing. All right. So, for example, a function is increasing here up until x equals 5. Why? Because if I take any two distinct points on the graph, the point on the right will be higher than the point on the left. That corresponds to an interval on which the function is increasing. Likewise, from 5 to 8, the function is decreasing because if you take any two distinct points on the interval, the point on the right is lower than the point on the left. And over here, the function is constant, at least piecewise. All right. So, a function can be increasing, decreasing, or constant on various intervals. Okay. I should say a continuous function will be increasing, decreasing, or constant. All right. Because obviously if he's jumping around, then it might be harder to classify things. Okay. And the idea is that we're going to use derivatives to determine when the function is increasing, decreasing, or staying constant, and then we're going to try to identify these kinds of points. So in a way, we're kind of going backwards. Here, we're actually going from these key points to interpreting what's going on around them. All right, we're going kind of backwards here. We're starting with the graph. Later on, we're going to draw the graph. All right. Now, first of all, we're going to draw the distinction between absolute extrema and local extrema. All right. So when I say big A, that's going to generally refer to absolute or global. Okay, that means that you're the biggest guy or the smallest guy overall. All right. L for local or relative. And I know some of you might be thinking, well, shouldn't it be absolute versus relative? Shouldn't it be global versus local? You could look at it that way, but for some reason, books tend to pick these two words. I don't know why we pick them together, but A for for absolute, L for local. All right. Although you can use absolute or global, you can use local or relative. All right. So let's look at these points one by one. All right. And I have some, some more comments in the notes, but I'll just briefly discuss why they are what they are. All right. So let's start with point B. All right. Now, judging from the graph, it appears that this guy is a king of his hill. All right. He's the king of his hill, meaning that P is a local maximum point. Okay. It appears that P is a local maximum point. Okay. Why? And this I don't want to write on the board. You should get this idea. Why is P a local maximum point? Okay. Why is it that 5 is a local maximum? Okay. So we say that 5 is a local maximum. And the value of F there is 10. The value of F there is 10. Bear in mind, books sometimes get kind of flaky, or they might kind of differ as to what exactly is a local maximum or a local minimum. Most books would say that they're going to be values for the independent variable like x, okay? But some books might differ. To make things easy, I'll tend to refer to the point, okay? So if I ask for the local maximum point, I want the x coordinate and the y coordinate. Okay. But most books would say that 5 is a local maximum, and then 10 is the local maximum value, is the function value there. Right. Now, why is it? Why is P a local maximum point? Why is x equals 5 a local maximum? Because, all right, get ready for this, there exists a neighborhood or interval containing x equals 5 on which 10 is the highest value. In other words, there exists an open interval containing 5. There exists a neighborhood of 5 on which this is the highest point. Okay? There exists a neighborhood of 5. Okay? For us, a neighborhood will be a symmetric open interval containing the number. All right? But there exists a neighborhood of 5 on which P is the highest point. Okay? So in that sense, he's king of his hill. He's king of his neighborhood. All right? Back in The Godfather, right? You have these old local kings of their neighborhoods, right? Okay? So he's king of his hill. So he's a local maximum. All right? However, based on the way I've drawn this thing, it looks like he's not only the king of his hill. Okay, like James Cameron, it looks like he's king of the whole world, right? I mean, based on the way I've drawn this thing, it looks like P is going to be the highest point in the entire graph. It looks like 10 is going to be the highest number in the entire range of the function, right? So, I think that P is not only a local maximum point, it's also a what? Also an absolute or global maximum point. Okay, so we'll say that we have an absolute maximum at x equals 5 as well, with function value 10, because it appears that this is the highest point on the entire graph. Okay? Now, as far as calculus goes, calculus is very good at identifying local behaviors, because we tend to do this a lot in calculus, right? So it's going to be easier for us to determine that P is a local max point. Okay? In order to determine that it's an absolute max point, we have to understand the overall behavior of the graph. And in principle, that's hard, right? I don't think it's hard to do. All right, the question so far, it appears that this guy's both. P is both a local max point and an absolute max point, or global max point. All right? Now, what about point Q? All right. Well, it looks like Q is a local what? Local midpoint. Okay, Q appears to be a local minimum point. Okay? In other words, 8 is a local minimum, corresponding to a function value of 3. Okay? The reason being that there exists a neighborhood of 8, right? A symmetric open interval containing 8. There exists a neighborhood of 8 on which Q is the lowest point. Right? So he appears to be a local minimum point. Does it look like he's an absolute or global minimum point? No, because there are points that are lower. It's like Schadenfreude. There are other people who are lower than you are. So we move over that. All right. So Q is not, but is not an absolute midpoint. For the simple reason that there are other values in the domain of the function where the function value is lower than 3. Okay, like over here the function value is 1. Over here we go negative. All right. Q is a local or relative minimum point. Okay, he's a midpoint relative to his neighborhood. And by the way, neighborhood is a technical term in math, you can look it up, right? But it's not an absolute minimum point. Okay, questions about that? So, sort of a local valley, but not the lowest point on the whole earth. All right. How about R? Okay, it looks like R is a what? It is a local or relative what? Max point, right? It looks like on a neighborhood of 12, on some neighborhood of 12, this guy's the highest point. So R is a local or relative max point. Okay, but is it like P isn't an absolute max point as well? No, for the simple reason that P, for example, is even higher. Okay, 7 is not high enough. 7 is not the highest function value in the whole range. It looks like 10 is. So, it's a local max point, but is not an absolute max point, or global max point. Okay, so this whole idea of absolute or global versus local or relative. Any questions? Any questions? Of course, if you take a point like this guy's nothing, right? It's not a max point. Okay, questions so far? Questions so far? Because there are some subtleties. Speaking of subtleties, what can we say about point S? Is point S a local midpoint? Our answer is yes. S is a local midpoint. Okay, because we say ties are okay. All right, that's sort of the informal principle here. Ties are okay. So let's say that you want to be the local midpoint. All right, you want to win the crown of local midpoint. All right, I know in Columbia there's an ugliest person contest, and I've seen photos of winners and they're very deserving. But yeah, this person wants to be the local midpoint. All right. Now, are these people going to steal the crown? No, this person's still a local midpoint. It's okay if there are people around here who are just as ugly as you are. Okay, so ties are okay. Okay, he is still the lowest point in his neighborhood, and ties are okay. Okay, so S is a local midpoint. Ties are okay. It's okay to have guys around you with function values as low as yours is. All right, but it's an absolute midpoint.
Yeah.
Look over here. Look over here. No, because these guys here, right? We have function values less than 1. We have function values that are negative. All right. So is a local midpoint, but is not an absolute midpoint because of these guys over here. All right. We have lower function values, less than 1. All right. Questions about that? S is a local midpoint, not an absolute midpoint. A local. Yeah.
I know you said ties are okay. Is that with local minimum only, or is it absolute as well?
Absolute as well. So if there's an earthquake, I didn't feel like I was sound asleep at 9:55, but yeah, if there's an earthquake, this guy moves up, that guy is a tie. They're both absolute max points. Okay, so you can have ties, all right? It does not strip away your title. Okay, now, by the way, why is this not a local max point?
Because
There are points immediately around him who are higher, okay? So if you look at a neighborhood, okay, there is no neighborhood of 14, and that means you need guys to the left and to the right. There is no neighborhood of 14 on which 1 is the highest value, okay, because you have values over here that are higher. I don't care how small you make that neighborhood, you have to have some space, right? Okay, delta's got to be greater than 0, right? You have to have some space in there. Okay, so the neighborhoods immediately to the left, they go higher right after that, so this guy is certainly not a local max point. All right, yeah.
In this graph, is S differentiable?
No, you don't need to have differentiability. Now, a lot of books would say that you need at least continuity to be a maximum midpoint. A lot of books would say that. Other books differ. Right. But a lot of books would say that you need to have continuity, certainly to be a local midpoint, and possibly even for absolute mid. Although absolute mid we tend to be a bit more liberal. Okay. So I'll say this. Personally, I feel that my own feeling is you need continuity to be a local midpoint. You don't necessarily need continuity to be an absolute midpoint. That's my opinion. But books can differ.
So why is it not a minimum point?
No, I'm saying S is a local minimum point, but it's not an absolute or global minimum point because these points here are lower. This is not the lowest point on the entire graph. Not the entire graph. These points are lower.
no any minimum point in there.
Yeah, the way I've drawn this, you're correct. He's right. If you assume that the graph extends downward as expected, you're correct. There's no absolute midpoint. I never said that you had to have these points. Okay. All right. Questions? Questions? How about T? Okay, now I know that T is not going to be an absolute maximum point, but what is T going to be?
It's a local max and
It's a local max and midpoint, I agree. Okay, ties are okay. All right. T is a local max point and a local midpoint. Okay? Because there exists a neighborhood of 16 on which T is the highest point, ties are okay. Also, T is the lowest point, ties are okay. So if you have a constant function, right? Constant function, right? Every point on there will be everything. Local max point, local midpoint, absolute max point, absolute midpoint. So the graph of a constant function, all those points will be everything. All four of those. Okay. We see that in this case here, T is not an absolute max point because of these guys up here, and it's not an absolute midpoint because of these guys down here. All right. So classify P, Q, R, S, and T. People normally do ask me questions about this. Okay. Any questions? Yeah.
So isn't everything in that case a local maximum on the minimum?
You're correct that all the points to the right of S will be both a local max point and local midpoint. S itself, however, this corner point, he is a local midpoint, but is not a local max point because the guys immediately to the left of him are going to be higher. Okay, there is no neighborhood of 14 on which this guy is the highest point because you can make this guy as small as you want. There has to be some space in there. Okay, you will have higher points to his left. Okay, so S is not a local max point, but it is local midpoint. These guys are both. Okay. And of course, these guys are not absolute anymore. Okay. Any questions? Let's get the terminology straight. Yeah.
so if when we're describing it, will we say like the limit or expect the function?
A limit. We're not going to talk so much about limits. No. It really is a matter of neighborhoods and are you the highest or lowest? Yeah. that's for the local behaviors. For absolute, that's more ambitious. You have to know what the overall graph looks like. You can see how it's going to be harder to classify absolute extrema because you have to know what the overall graph looks like. It's easier to classify things locally, as we'll see.
Is there
Okay, right. Yeah.
is there notation like the function value as it
No.
approaches from the negative?
No, we don't have clean notation. We just describe them.
Okay.
Yeah. In fact, books don't even, like I said, the idea of a local maximum, books even disagree a bit. Most American books say that 5 is a local, in fact, it's an absolute and local maximum, and the corresponding local maximum value and absolute maximum value is 10. But again, some books kind of differ on that. Okay, that's why I tend to ask for the point, because if I ask for the local or absolute maximum point, there's no ambiguity. You just say 5, 10 in parentheses, and that's uncontroversial.
And if there's no negative line on the left side, that goes.
So if there were no points over here, you mean?
Yeah,
Okay.
then are those both X and T are
They
minimum point?
they will be local and absolute minimum points. Yes. So if I cut the graph here or higher, okay, then you're right. These points would be local and absolute min points. Okay. Remember, for the absolute designation, for me to call them absolute, I have to look at the whole graph. Okay, I have to ask, is 1 the lowest number in the range? Okay, if I have this graph, the answer is yes. If this is the graph, the answer is no, because I have lower numbers in the range. So range, that's actually an important question. And that's especially important with absolute maximum and minima, because then you're asking for the extreme values of the range, if there are any. If there are any.
I still don't see how like it's the limit of maximum for T.
Okay, well, L is for local here. Local.
Or local, I mean, why is it max though? Because it's,
Why is T a local maximum point?
yeah.
Okay, because there exists a neighborhood of 16, for example, this one. Okay, by neighborhood, I mean an open interval containing 16, which means that I have to include values of x immediately to the left of and to the right of 16. Okay, right. But 16, right? They're all ties, okay? 1 is the highest function value on this interval. In fact, it's the only function value on this interval. That's okay. Ties are okay. This is a local max point because there are no points around him who are higher. That's one way of looking at it. He's a local max point because there are no points immediately around him who are higher. You could not say that about S, because as soon as you move a little bit to the left, right, 14 minus delta, whatever, okay, then this has to go higher. Okay, so T is a local max point, S is not. All right. And again, this is all very subtle, and I always get questions about this. Questions. P, Q, R, S, and T. You understand why they are what they are, and they're not what they're not. Any questions? Any questions? Bear in mind, this is a really weird function because it's got to be like, piecewise or something weird. No polynomial that's not a constant flattens out like that.
Do we get into anything like epsilon and delta, like in limits you have a precise definition and you have like a threshold? Do we really go over
In chapter 4, not really, no. We're going to fall back on our old ideas of continuity and differentiability. So no, you're probably not going to see too much of delta and epsilon. I could have done that stuff here if I wanted to, but I didn't want to go that deeply. I just use it from neighborhood, just as a catch-all for values of x that include numbers that are immediately less than and greater than the number of interest here.
So if you have a graph that goes to infinity in either direction, then you're not going to have an absolute in whatever direction it's going.
You're not going to have an absolute maximum.
Yeah, maximum one.
Minimum. Let's say you have a snake. Let's say you have a cubic. No cubic will have an absolute max point or an absolute min point.
Okay.
Now, if you start restricting the domain, and we're going to get to this, then yeah, you might have an absolute max min. In fact, you will. Okay. Question. All right. So, Alice's discussion sort of brings us to an idea. Are there sufficient conditions under which we're guaranteed to have absolute extreme? And there are. We'll talk about that next time. Next bad place. Any more questions? Speaking of which, and people have brought this up before. Oh no, I do one more move. There we go. All right. Wait a minute. Wait, don't. All right. This is what I want. This is what I want. Okay. So this could be like a 6 degree or worse. All right. Now, if I drew it right, okay, apparently. Okay, let's look at this thing. All right. This was like Michigan went through a big earthquake or something. All right. How many absolute max points do I have? 2. Okay, I wanted these to be ties. We don't want to get there, but okay, so we have 2 absolute max points. Okay, 2 absolute or global max points. Okay, and I'm assuming that the graph is extending as expected, so no surprises. And if you do a good graph of a function, you're not supposed to get any surprises down the way, no sudden turns or anything. Okay, so I'm assuming that the graph extends as expected. All right, how many local max points? 3. 1, 2, and 3, right? Okay, so I say 3 local max points. How many? Okay. How many absolute min points? Looks like none. Yeah, 0 absolute min points. No one said you have to have any. Okay, no absolute min points. How many local min points? Looks like 2. 1 over here and 1 over here. Yeah. Okay. 2 local min points. All right. Questions about that? All right. Ties are okay. You can have 2 absolute max points. That's okay. Now here's something that's a little sneaky, and you have to remember the definition. Let's say that I have a graph that looks like this. Here's the point 6, 2. All right, this is the entire graph of the function f. Well, I mean, this guy can extend. Right? Okay, now we assume that it extends as expected. If there are endpoints, we clearly indicate those. All right, now here's my question to you. Well, based on the way I've drawn this, there are no local or absolute max points, right? Okay, first of all, does it appear that P is an absolute midpoint?
Yeah.
Yes, I agree. Okay, so I agree with you that P appears to be an absolute minimum point. Now, here's the $25,000 question. I'm not going to give it to you, but is P a local midpoint? The answer is no. Why not? There's, okay, you know, yeah, continuity, yeah, I would, and a lot of folks would say we don't have continuity there. In particular, there's nothing to the right, okay? There is no neighborhood of 6 on which the function, throughout which the function is defined even, okay? There are no values of, basically the domain stops at 6, right? There are no values of x even slightly greater than 6 that are still in the domain, all right? If you have no neighbors to the right, look, let's be fair. In order to be a local extremum, you have to have neighbors to your left and to your right. If you don't have any neighbors to your right, no fair. You're not a local anything. You can be an absolute min, okay? And remember, there are fewer conditions for that. I mean, I can have some like fractal thing, right? Okay, we can talk about absolute max and min, but local is more subtle. Okay, so we say P is an absolute min point, but not a local min point. Why not? Because we cannot say that P is the lowest point on a neighborhood of 6, because there is no neighborhood of 6 throughout which the function is even defined. And a neighborhood requires that you have values in the domain immediately less than 6 and greater than 6, if you're going to classify 6 as a local extremum. Questions? Do you see that? Yeah, huh?
So we don't really have like a one-sided local minimum or something
No.
like that? Okay.
No. The bottom line, I'll ask you, is this an absolute midpoint? Yes. Is that a local midpoint? No. Bottom line. And like I was saying about continuity, a lot of books require continuity. And in fact, I'm tempted to as well. Yeah. When I call something a local midpoint, I assume continuity there. Yeah. Because when I say neighbors, I mean touching you as well. So I don't want to sound legal or anything, but okay, your neighbors have to touch you. Okay, good to that here. Okay. Okay, so I require that we have continuity for a local extremum. Although again, some books even are kind of laughing at that. I think even Stokowski is kind of laughing at that. But I'm not going to push on that issue anyway. Okay. All right, fair enough. So watch out for endpoints. Okay, we generally don't. When we have that kind of endpoint behavior, okay, the idea that it can be a local extremum often falls off a cliff. Unless you have like a piecewise guy that miraculously takes up where you start or something, where you stop or something. Okay. Questions? P is an absolute midpoint, but not a local midpoint, because there are no neighbors to the right. Okay, and you can make a continuity argument. Speaking of Alice's question, under what conditions do we have absolute extrema? Well, we talked about the IVT back in chapter 2. That relied on, what did the intermediate value theorem rely on? What nice property of functions? We liked it if functions were defined, and then what? Yeah, what's the C word? Continuous, and in chapter 2, right? So what's another benefit of continuity? All right, this takes us to the EVT, the extreme value theorem. Okay, before the IVT guaranteed the existence of intermediate values between the endpoint values, right? Here, we're going to guarantee the existence of absolute extrema under certain conditions. So these are sufficient but not necessary conditions. We don't need them, but if we have them, we're guaranteed absolute extrema. All right, if f, or whatever, g, h, whatever, but if a function f is, again, continuous, right, keyword, if f is continuous on a closed interval, and there's also a key word here, a closed interval, a comma b. For now, I'm assuming that a is less than b. Okay, later on that will change, but for now let's assume a is less than b. If f, otherwise that's an empty set. If f is continuous on a closed interval, okay, brackets a comma b, then there exists, you use that backwards e, then there exists absolute maxima and absolute minima, okay, on that interval. Meaning that there exists an absolute maximum point and an absolute minimum point. When I refer to absolute maximum and minimum here, I'm referring to like the x values, right? So, under these conditions, we're guaranteed again an absolute maximum and an absolute minimum somewhere on that interval. All right. Okay. I'm thinking technically it would be in, but that's fine. In, on. All right. Okay, example. Okay. All right. f of x equals 1 over x on the closed interval from 2 to 5. Okay. Let's talk about the graph of this function. Now, as far as we're concerned, this is the restricted domain. This is the entire world. Okay, it's a restricted domain. It's your entire world. There's nothing outside of it. Okay. The graph of y equals 1 over x. Now, here's the thing. You agree that on that interval, it's a nice graph. Now, you might be going, isn't there a VA? Yeah, but where's the VA? Where's the VA for y equals 1 over x? X equals 0. Well, who cares? that's not in restricted domain, right? We just care about what's happening from x equals 2 to x equals 5, right? Between here and here, it's a perfectly good graph. Okay, over here, now this is not to scale, but or different scales. Okay, so this is going to be 1/2 or 0.5, right? Over here, this is 1/5 or 0.2, right? 0.5, right? To the endpoint, and we get this slide. You agree? The graph of the function on that restricted domain is a perfectly nice slide, right? No VAs, nothing wrong with it. All right, nice and continuous, no problems. All right. You agree here that the function is continuous on that domain, right? It's not continuous everywhere, but it is continuous on that restricted domain. Okay. So observe f, because it's rational and only 0 is a problem. F is continuous on the closed interval from 2 to 5. Okay? Therefore, by the extreme value theorem, what must be true? There must exist what? An absolute maximum and minimum. Okay. Therefore, there exists an absolute maximum and under this, and there exists an absolute minimum somewhere in that interval. Okay? We'll take a look here. Where's our absolute max point? Well, you're here. The absolute max point is going to be at 2, 1/2. Right? Here's our absolute min point. Okay, that's at 5, 1/5. Right. In this case, they're at the endpoints of the graph. That's not always the case, but you know it's often the case, not always. But here, our absolute extrema are at the endpoints. Question: Are these also local max and min points? No, right? Because that whole open interval neighborhood thing, right? This guy has no neighbors to the right on this interval. This guy has no neighbors to the left on this interval. Okay, so they're not local maximum points, but they are absolute maximum points in context. Okay, on that restricted domain. Yeah.
So, since it's a slide, does that mean that there isn't any local?
Oh, right. Because just because we know what the graph of this looks like, there are no local maximum points inside here. Just because we know what the graph of this looks like. And you can verify that, especially when we talk more about chapter 4. Okay, when we take the derivative, there's no place in there where the derivative is 0 or dne, so it can't do anything like turn around or something like that. We'll talk about that. calculation of the EBT. Right. Yeah.
Would we ever be given an open interval for a restricted domain?
Yeah, well, yeah, let's talk about that. Could be any question. That's the next example. F of x equals 1 over x. What if we have the open interval? Alright. So that's the restricted domain. Question. Does the EBT apply here? Not on this interval, okay? So I have to warn you, the extreme value theorem does not apply, at least to this open interval. Okay, because it's an open interval. Or more precisely, it's not closed. The set of all reals can be called both open and closed. So I want to point out, this guy is not closed. All right, that is not a closed interval. In fact, it's a purely open interval, not closed. Okay. Now, does this mean that this cannot have absolute maximum minimum? Well, not necessarily. It just means that the theorem doesn't apply. Okay. So it's still an open question. Okay. Are there absolute maxima or minima? We don't know yet. Okay. Just because the theorem doesn't apply doesn't mean that these can't exist. It depends on the situation. Right? So, question, what is going on here? Do we have absolute maximum and minimum? We don't know yet. Oh, the theorem doesn't apply. It just means that we don't have the security blanket. Okay? We're not sure. So we got to think about the situation. Not the situation, but we think about you don't want to think about him. Right. Okay. How does this graph differ from that graph? Open circles, yeah. The endpoints are not included on the graph. Okay, the endpoints are not included on the graph. So here's 0.5, right? Here's 0.2. Here's the graph left. Now here's the problem. Let's say that we're looking for an absolute maximum value, okay, like a function value or y-coordinate. Imagine Bart and Nelson from The Simpsons. Okay, they're competing, and they're trying to get the point with the highest y-coordinate, right? Yeah, exactly. All right. So Bart picks a point where the y-coordinate is 0.49. What can Nelson say? Okay, I was calling you then. All right. Nelson picks a point with y-coordinate 0.499. What can Bart do? 0.4999. What can Nelson do? 9999. What does he say? All right. They keep playing this game, right? They keep climbing towards that point, but can either boy actually pick this endpoint? No, it's not a point in the graph. So you agree, there is no absolute maximum here. Now, this is bounded, right? The function is bounded, but there's no absolute maximum because neither boy is allowed to pick up the 0.5. You can get arbitrarily close. This really is a calculus idea. You can get arbitrarily close, but you can't hit the 0.5. Right. So there's no absolute max value. Likewise, there is no absolute min value. You can't pick up the 0.2. Right? So this has no absolute extreme. And of course, this guy, there's no waviness inside here, right? There is no absolute maximum, nor is there an absolute minimum on this entire interval. Okay, there is no highest value, there is no lowest value, although he is bounded. Right? Broadly speaking, the function values are bounded. Yeah.
That's because there's holes, right?
Yeah, the holes are a big part of that. Yeah, because you're not allowed to pick. You're not allowed to pick the hole. You're not allowed to pick the hole. You can pick the point here, pick the point here, but you can't pick a hole. Right? Questions? Questions? So bear in mind, even when a function is bounded, right, in value, you might not have absolute extrema. Okay, because you know how you play this game. Okay.
Real quick,
Yeah.
if we go back to this other example on x.5, that's the absolute min.
Yeah, yeah.
Right.
So we have an absolute minimum at x equals 5. The absolute minimum point is 5, 1/5. That's
Even though there's nothing on the right side of that, is it because it's a closed interval?
Yeah. For absolute extreme, we don't care about neighbors.
Okay.
consists of a single dot. I say, hey, that's an absolute max point and an absolute min point. That's what I say.
But no local.
But no local, because he has no neighbors.
Right.
He's all alone. Okay, questions? How about this guy on the close interval from -1 to 1? Question, does the EDT apply here? No.
Negative.
Is the function continuous on this?
No.
No. Where's the problem?
Zero.
At 0, okay? Here's the problem. F is discontinuous at 0, right? F is discontinuous and x equals 0. Okay, meaning that he's not continuous on the interval. This means that F is not continuous on the interval. If you have even a single discontinuity on here, you're dead for the whole interval, okay, in terms of continuity. Which means that the EDT does not apply. Now again, just because it doesn't apply, doesn't mean that we cannot have absolute extrema. Well, no, not necessarily. It just means that we don't have that insurance, right? We don't have that guarantee. Okay, the EBT represents a guarantee. Okay, it's like a warranty that actually works out. Right. Okay, the EBT does not apply. So let's see what happens here. What do we have at x equals 0? We have a big A. Okay. And what's going on here? Well, let's see. We have this guy going down to the point 1, 1. Right? And then we have this piece over here going up to the point -1, -1. Okay? So that's the graph of F. Okay? So look at this graph. Is there an absolute max point? No, because it goes up, 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 up without that one. Is there an absolute midpoint?
Yes.
No. Down, down, down. You go -1 million, -1 billion. Okay? The range is unbounded in both directions. Okay? You can go arbitrarily high or arbitrarily low. Is this a local midpoint? No. Is this a local max point? No, because of the neighbor argument. Okay? There are no neighbors that we care about to the right over here. No neighbors we care about to the left over here. We don't care about anybody outside of our neighborhood. We're very provincial. So, you know what? We have no extrema. I know it might sound kind of strange, but we have no extrema of any kind. Okay, this is not an absolute midpoint either because of all these guys. Okay, this is not a local max point. I'm sorry, this is not an absolute max point because of these guys. We have no extrema whatsoever. Although it is interesting that these are endpoints. That is kind of interesting. Questions? And another example. All right. Example. F of x equals, hey, sine of x. Some trig finally. On the open interval from 0 to 2 pi. Now, does the EBT apply to this function on this interval? No. Okay? Observe that this is not closed. Okay, it's an open interval and it's not closed. Alright? So the EBT does not apply. Okay. Does this automatically eliminate the idea that we have absolute extrema? No, not necessarily. No, we could still have it. That's a question mark though. Are there any absolute extrema? Right now, that's a question mark. Okay, the fact that EBT does not apply, it means that we're just not guaranteed them. But at this point, we don't know. We just have to look at the situation. Look at this case. I know it doesn't look like it, but if I rip over my shirt, I really have to deal with the situation. I really have to rip all rip. Right. You ever see, what was it, Shaolin, what was it, Shaolin soccer or something? It's just like this guy calls out guys to beat him at soccer, and he picks up this little guy turns up to All right. All right. What does the graph look like? All right. we have an open circle here, goes like this, open circle here. So this is at 0, this is at 2 pi, here's 1, here's negative 1. Now here's my question. On this interval, does the function have an absolute maximum? Yes, it does. You see what it is? What's this? Pi over 2. Yeah, pi over 2, 1. Okay, that is an absolute maximum point. Okay. On this interval, bear in mind, if we consider all reals, we have infinitely many. If we consider the domain as all reals. Right? Okay, do we have an absolute midpoint? Yes, we do at 3 pi over 2. Yeah. Okay, so at 3 pi over 2, negative 1, we do have an absolute minimum point. Alright. So, even though the EBT didn't apply, that still didn't stop us from having absolute extrema. It's just that we didn't have a what? We didn't have a guarantee. We didn't have a guarantee or a warranty for all this.
Also local, right?
Yes, that's right, also local. Also local, that's one. But bear in mind, the EBT guarantees the existence of absolute